Okay, so we're going to continue, as I mentioned before, for the next few lectures. We'll be talking about paths through graphs. And so today we're going to start talking about one particular special type of path and analyzing it in some detail. But before I want to do that, I just wanted to point out a few corrections from the last lecture, a few small mistakes that I made. So the first thing to point out is in this example, where I was counting the number of paths through this particular directed graph, I mentioned there was only one path from U to Z, and someone pointed out that that's not the case. For example, you can start at U and then go from U to X and then X to Y, which is how the path began, but then you can go back from Y to U, or you can loop around U, X, Y to U, and you can do that as many times as you like. So you can actually create a path of arbitrarily large length. And then when you finally want to go to Z after looping around a few times, you go to Y and then W and then Z as I did here. In fact, now I'm also noticing I just left W out as well from what I read here. So the correct thing to state that doesn't make this statement precise is, and this is related to what we'll be talking about today, is that there's only one simple path from U to Z. And so remember, a simple path is a path that doesn't traverse the same edge more than once, right? So if you add in this extra condition simple, then the statement is correct. So I apologize about that. Right, and then one more thing to point out, which I already emailed everyone about. So if you go to this example when I was talking about circuits, well, you can see if you look at G for a little bit, there is a simple circuit of length 4. What I really meant to say, but I was reading my notes incorrectly, is that there's a simple circuit of length 3 in H, right? So if you look at the triangle at the top of H, this is a simple circuit of length 3. But if you look at the graph G, there's no simple circuit of length 3. So this really should have been 3. So I apologize about that as well. Okay then, so looking forward, right, as I just mentioned, we're going to be talking about particular types of paths through graphs, right? So there's this general problem where you're given a complicated graph and you want to understand the different paths through the graph. This problem shows up in applications in a variety of places. Maybe we'll talk about some of this next week. Right, so we want to talk about paths through graphs. And so there's a sort of a classical problem in math where this problem arises, and this problem actually led to the introduction of graph theory and the way we think about it now. And so this is something that's known as the Königsberg bridge problem. And so the problem is the following. So I'm going to draw like a rough sketch of a town which was formerly known as Königsberg. So it was in Prussia, which no longer exists. So it's now somewhere in Russia. I don't know exactly where in Russia it is. So there's this famous problem. So let me draw a sketch of the map of the town. So there's a little island in the middle of the town. Right, so C and B are maybe some river and some island A, river between points C and B, and some island A in between, and then maybe some peninsula, which I'll call D. Right. And so you want to imagine that the space in between B, A, C, and D is all water, right? And so you have a few bridges that are connecting the different land points. Right, and so these are a rough sketch of the bridges. Right. And so the problem is the following. So if you start, is it possible to start at some location and travel across every single bridge without crossing the same bridge twice. Right? Right, so let's say you want to start, say, here. And so the question is, well, okay, I can cross through this bridge. Maybe I can cross through this bridge and then loop back, right? But I can't go from this point back to B because then well, maybe I can continue doing this, right? So I go down to B, and then I can continue this way. I cross up to D. But once I'm here, no matter which way I go, I'm not going to be able to. There's two remaining bridges I want to cross. And so there's no remaining path I can find where I don't cross one of the bridges I already did, right? So this would be a bad route, which does not solve the problem, right? And so, right, so this problem was posed in the 1700s, I think, and it was solved by the mathematician Euler of the Euler number fame. Like this is the person who the number E is named after, and he basically invented. Maybe didn't invent graph, but this is one of the first major uses of what we now call graph theory to solve a problem. And so, well, how would you model this using graph theory? Well, you can use something called a multigraph, which we briefly talked about earlier. And so a multigraph is just a graph G where you're allowed to have more than one edge between vertices, right? Right, so multiple edges are allowed between two vertices. Right, and so what does this look like from a graph theory perspective? Well, you can let the edges be the bridges. And so and the vertices are the different land pieces. Right, so I have landmass B, landmass A, landmass C, and landmass D. Right, so if I draw this picture, well, let's C is up here, A is over here, B is down here, and D is over here. Well, I have two bridges from A to C, so this will be the first bridge and this will be the second. And then I also have two bridges from A to B, right? And then I have a bridge from A to D, and then finally a bridge from C to D and a bridge from B to D, right? And so the question is, well, if you start, one way to rephrase this problem in terms of graph theory is if you start at any vertex, is it possible to find a path through the graph for which you do not traverse the same edge more than once, right? So the bridge becomes an edge now, right? Right, so let me write that out on the next slide. Okay, so let me just copy the picture up over here. And so the graph theory version, right, so is it possible to find a path through this graph starting at some vertex and ending at the same vertex that does not traverse the same edge more than once? Right, so we've converted this problem about crossing bridges into a graph theory problem about multigraphs. So one thing to point out is, well, I'm talking about a path that starts and ends at the same vertex. So remember, these are called circuits. Right, so we're asking if it's possible to find a circuit that does not start and end at the same vertex, but travels through every single edge. a circuit that starts and ends at the same vertex, which is what a circuit is, but we want the circuit such that you do not traverse the same edge more than once, right? And so remember, in graph theory terminology, we're really looking for a simple circuit, right? Because simple means that you don't travel the same edge more than once along the path. Okay, so we're looking for a possible simple circuit. Through the graph. Right, and so such a circuit has a particular name, and because of this problem, it's actually named after Euler. So an Euler circuit in a multigraph is a simple circuit that contains every single edge of the graph. Right, and so the problem, this bridge problem can be rephrased in modern language as just asking, given the graph that you see in the top left corner, is there an Euler circuit through the graph or not? And that's what the bridge problem becomes in modern terminology. One thing to point out is that you don't just have to talk about circuits, right? So it also makes sense to talk about Euler paths. And so an Euler path is going to be, instead of a circuit, just a path through the graph that does contain every single edge, right? So maybe it starts and ends at a different point, but you still want to traverse every edge exactly once, right? And so we'll talk a little bit about Euler paths at the end of the lecture, but for now we're going to focus on the problem of circuits. Right, and so, well, how did right, so the reason these paths are named after Euler is because he came up with the solution to the problem we've introduced. And so how did he actually solve this problem? Well, the idea is to imagine that you actually had an Euler circuit through the graph. Right? Right, and try to understand, well, how does this path cross through each vertex in the graph, right? So suppose we had a circuit, in particular a simple circuit in G, and let's say it starts at A, right? So let's say A is the vertex where the circuit starts. Well, notice, so suppose first that I have some vertex V which is not equal to A, right? So I have some different vertex that's along the path somewhere else in the graph, right? So maybe this is V over here. And so now let me use the blue to denote the path. Well, the path is crossing some number of vertices and then it hits V. But as soon as it hits V, it has to go through V because V is not the endpoint, right? Since it's a circuit. And so notice that as soon as it crosses through V, well, what happens to the degree of V? The degree of V has to be at least 2, right? And so maybe it travels along and goes into the graph, and then maybe it crosses through V again, through different edges. But if it crosses through V again through different edges, it still adds 2 more, right? And so in particular, the degree of V has to be even if this is going to work. Right? Because every time the path crosses through V, as long as every time it passes through V, it's not crossing through one of the edges that you previously crossed through, it always has to contribute a count of 2 to the degree. And therefore, the only way this can happen is if the degree of V is even. Right, so for example, if I had such a path, right, let me travel along the red, let me travel along the blue with a red path instead. if I had such a path and I did not contribute an even number to the degree count, well, the only way for this to happen, if you look at this picture, is if instead of going along the blue path, I cross through one of the edges I already crossed through, right? So it's possible to have a circuit that through a vertex of odd degree, but the only way for this for the path to cross through a vertex of odd degree is if eventually you repeat one of the edges, right? So the only way to avoid repeating one of the edges is if you have an even number of degrees, right? And so therefore, any vertex in the graph, if you have a simple circuit, any vertex that is not the starting point has to have even degree, right? So that's a very important property that we'll be using a lot today in the lecture, right? So therefore, what we've just showed is that if I have some vertex v, which is not equal to a, right? So a was the starting point. Then v has even degree. Okay, and so, well, we've shown that every single vertex in the graph has to have even degree, except possibly the starting point. So let's suppose now that the vertex v is equal to a, or v is the starting point. So I'm going to claim that it also has to have even degree, right? And so why is this? Well, once again, we have our circuit that leaves a and travels along somewhere into the graph. And so eventually it's going to, since it's a circuit, it's going to come back to a, right? And so therefore, right, as soon as it comes back to a, the degree of a has to be 2. Well, now it's possible that it continues, right? Well, the only way for the path to continue, if it's a simple path, is if there's another edge that points out that's not one of the two that we already saw. So maybe the path goes along like this. But again, since it's a simple circuit, eventually it has to come back to a. And so if it eventually comes back to a, it has to end at a, and so it's going to, again, contribute a count of another 2, right? And so this could happen several times, but eventually once you get to the terminal point of the path and it doesn't continue anymore, each time you've gone through a, you've added a count of 2, and so the degree of a also has to be even. Right, where remember a is the starting point of the circuit. Right, and so what we've just proved is the following theorem, which was originally observed by Euler, which is why these paths are named after him. And so the theorem is that suppose you have well, for technical reasons, you need your graph to be connected, which I wasn't really mentioning before, but if you have a connected multi-graph G, and G has an Euler circuit. Of course, Euler did not call them Euler circuits. We're just using the more modern terminology. But right, if you have a connected multigraph with an Euler circuit, then every vertex has even degree. Right, and so, well, what's the consequence of this theorem? Well, the consequence, if you go back to the Königsberg bridge problem, the answer is there's no solution, right? Right, why is this? Well, let's go back to the picture on the previous page. Well, let's look at let's look at the degrees, right? So C has degree 3, D has degree 3, B has degree 3, and A also has degree, well, no, A has degree 5. And so in fact, this fails dramatically because every single vertex has odd degree. What the theorem says is that you need every vertex to have even degree, and this is like the worst alternative where every vertex is an odd degree. And so there is no Euler circuit. Meaning the answer to the original problem is that no, there's no way to start at one point and travel along all the bridges without crossing the same bridge more than once. Right? And it really just follows just by counting degrees and observing that, keeping track of what the degrees have to be if you were to have such a path. Right? Okay, and so, right, so this is a pretty well-known theorem. And so, well, one thing you may ask is, okay, so we know that if a graph G with these properties has an Euler circuit, then we know that every vertex has to have even degree. And so the next question to ask is, well, suppose I just gave you a graph and you know that every vertex has even degree, right? You can see the picture and you can check that every vertex has even degree. Well, under this additional assumption, is it possible to solve the bridge problem, right? So is it possible to find an Euler circuit through the path? And so this is what's called a converse of the theorem we just proved. And so this is what we're going to talk about next. And so it turns out that this actually is true. Right, so the converse is the following theorem. Right. So suppose that G is a connected multigraph. I mean, for most of the examples we'll look at, other than the bridge problem, you can just think of it as just a regular undirected graph. But if you want to, it can be a multigraph. And suppose that every vertex has even degree. Right? Then you can always find an Euler circuit through the graph. Right, and so notice this is different than the theorem we just proved. Right, the theorem we just proved was the following. It said that if you have an Euler circuit, then every vertex has to have even degree. What we're going to prove here is what's called the converse of this, which is like the other direction, which is if you know that every vertex has even degree, then you can always find an Euler circuit. Right, so let's go through the proof. Right, and so how are we going to prove this? Well, we're going to proceed by induction on the number of vertices in the graph. And in fact, we're going to use strong induction for reasons that should become clear later. Right? So induction on the number of vertices. Right, and so for the base case, well, it doesn't really make sense to talk about this problem when there's only one vertex because then one vertex because then there's no edges. So in the base case, we'll consider the case when the cardinality is equal to 2, right? This problem really only makes sense when there are at least 2 vertices. And so in this case, right, we have to have some connected multigraph with 2 vertices such that every vertex has even degree, right? And so notice I can't just have one edge between the two vertices in the graph, right? For every, I mean, the edges have to come in pairs because otherwise each of the vertices would have odd degree, right? So for example, maybe the graph looks something like this, or right, since we're using multigraphs for this problem, maybe there are 4 edges, something like this. Well, in any case, you can always just see directly how to find a circuit, right? For example, maybe I start at the vertex on the left, and I travel along the first edge, and then I travel back along the second edge, and that's an Euler circuit. What if there are 4 edges? Well, I can continue this process and just start at the inner edges and then move to the outer edges, right? So I could go from here to here, and then back, and then now do the same process along the outer edges, and I can do that to find my circuit, right? And so if there are only 2 vertices, the picture has to look like this, and hopefully it's clear how you can construct a circuit. And so this forms the base case for our argument, right? And so for the induction step, we're going to assume the theorem holds whenever the cardinality of the vertex set is, say, smaller than some number n, right? So we can always use this theorem as long as the number of vertices meeting as long as we have a graph with fewer than n vertices which meet the hypotheses of the theorem. And so we're going to fix a graph G with vertex set cardinality n, which is connected multigraph and all vertices of even degree, right? And we want to prove that we can find an Euler circuit, right? And so we're gonna look at this proof as kind of an algorithm, like sort of look at it in an algorithmic way. And so the algorithm is the following. So fix an arbitrary starting point for your circuit. Right, so I'll pick some starting point A in the vertex set. And what I'm going to do is I'm going to keep traveling along edges until you can't anymore, right? So keep traveling in a path along edges until you can't anymore. Right, and so what does it mean that you can't travel anymore? Well, it means that any of any potential edge you could travel along has already been traversed, right? So right until you hit a vertex such that every edge leaving that vertex has already been traveled. Right, and so it may help to draw a picture to understand this a little bit. So let's say this is our graph G, right, and say A, this point A was picked as our starting point. Right, so maybe this is the graph we're working with. And this is a good picture to have in mind for the proof. And so maybe we picked A as our starting point, and we moved, again, you pick A, and then you just kind of arbitrarily keep adding edges to form a path. Right, let's say I went from A to F, and then F to C, and then C to B. Well, once I hit B, there's only one more edge I can add without traveling the same thing more than once, so I have to go back to A. And at this point, the algorithm would have stopped because I have no more edges I can travel, which I haven't already traversed, right? Right, and so I'm going to let V in my vertex set be the stopping point. Well, there are a few cases to consider. The first case is, well, if every edge in the graph is traversed and V is equal to A, well, then we're done, right? So from the picture that I just drew, you can see that this doesn't necessarily happen, right? So what we have to do is understand the case where you don't hit everything in the graph, right? So case 2 is where every graph in the edge is not traversed. Or sorry, every edge in the graph is not traversed. And so, right, so the picture I just drew is an example of case 2. So the one thing that we can use to our advantage, so notice in case 2, well, we ended at the same point that we started at. And so you may wonder, well, if this algorithm stops and you don't hit everything in the graph, did you at least produce a circuit, right? Did you at least end at the same place that you started? And it turns out that this is the case. So let me write this as a claim. Right, so suppose algorithm, meaning the algorithm that I described on the previous page, suppose it terminates at V. The claim is that V has to equal A, right, where A was the starting point, meaning this algorithm always produces a circuit, right? And so what is the proof of this claim? Right, well, recall that if V is not the starting point, we discussed earlier in the lecture that the path always has to cross through V an even number of times. Right, so for example, maybe this is my V, maybe the path did this, and then maybe it came back and did something like this and continued, right? So it always has to cross through an even number of times. Right, so the second thing to think about now is, well, what can the picture look like if the algorithm terminates at V? Right, so let's suppose that the red is the path that we've traveled already, so maybe it goes through V like this. And then maybe it comes back, and the blue is so the blue edge is the last edge that's added, right? So this is where it terminates. Right. So this means that well, every other edge leaving V has already been traveled. Right. And so, well, the only way this can happen is, well, remember, look at this picture. The picture I drew, in this picture, V has an odd number, odd degree, right? So since I'm assuming that V has an even degree, it has to look like this. And so therefore, right, so since V has even degree, there must be an odd number of edges leaving V that were already traveled. Right, because otherwise, if there were, right, so the last edge, like imagine deleting the last edge, or imagine deleting the edge where the path ends. Since V has even degree, if you delete that edge, there's an odd number of edges left, right? And therefore, there were an odd number of edges leaving V that were already traveled. But that can't happen unless V is the starting point, right? Just because of the previous bullet point, right? If V is not the starting point, then there's always an even number of edges that pass through V when the path travels through V, right? And so the only way where this can terminate with V having even degree is if V was also the starting point, right? And so that's the proof that V has to equal A, right? And so this at least tells us that the algorithm that I discussed on the previous page, where you just fix an arbitrary starting point in your graph and you travel along kind of arbitrarily adding whatever edge you can. It's kind of like a greedy algorithm type thing. When this terminates, you always produce a circuit. And we're essentially using the fact that every vertex has even degree, right? So if you look at the proof I wrote out for this claim, we're using the fact that V has to have even degree. And so this is where the proof would fail if you had a vertex with odd degree, right? And so this shows that we're in a situation like what I have pictured in the top left corner, right? When you run this algorithm, you may not hit everything in the graph, but if you're in case 2, you at least produce a circuit. And now the idea is, well, let's imagine that imagine you just pretend that the red path isn't here, right? So imagine like you delete the red circuit, which was produced by this algorithm. Well, then I have 2 graphs of, notice that in for this example, I have 2 disjoint subgraphs of smaller size for which I can apply the induction hypothesis, right? So I have the graph FG, oh, sorry, I forgot to label. Let's call this H. Right, I have the graph F, G, and H, and notice that every vertex in this graph, this subgraph, has degree 2. And so by the induction hypothesis, I can always find an Euler circuit. And similarly, in the other piece, CED, every vertex has degree 2. And so then by the induction hypothesis, I can find another circuit, an Euler circuit. And what I can do is I can piece these circuits together, right? I can travel from A to F, and then F to G, G to H, H to F, right? I can join this circuit to the blue circuit to the red circuit without any overlap among the edges, right? And then I can travel from F to C, and then C to E, E to D, D to C, and C to B, and then continue along the previous one. And so this is how the argument will work, right? So we're going to delete the circuit produced by the algorithm, and the remaining pieces of the graph will have smaller cardinality for their vertex set, and so we can use the induction hypothesis to find circuits. Right? So that's what we'll do now. Right, so next, what we're going to do is delete the circuit from G obtained from the previous algorithm. Right, and so you have to be a little careful when you talk about deleting things from a graph. So what do I mean? I mean remove all the edges from the circuit, and also all vertices along the circuit which were not incident with other edges, right? That were not on the path, right? So I only want to remove vertices that are not incident with edges not on circuit. Right, so if we go back to the previous picture, I'm going to remove all the edges that have a red arrow along them, but I don't want to, I also want to remove vertex A and vertex B, but I don't want to remove F or C, because F is connected to G by an edge, and C is connected to E by an edge, for example. And right, I don't want to delete those because they're connected to other parts of the graph, which our original path did not touch. And so if you remove the circuit in this way, this produces a subgraph G tilde, let me call it G tilde of G, with a smaller number of vertices. Right. And so we're going to apply our induction hypothesis on this graph, right? So for example, in previous example, G was transformed using this process to G tilde, which looks like this. So it's broken up into two pieces. Right. And so now what we'll do is apply the strong induction hypothesis to each connected component of this new graph G tilde, right? For example, in our picture, there are two different connected components, which gives us an Euler circuit in each piece. Right. And then once we find an Euler circuit in each of the connected components of G tilde, we can join them together, right? So join these circuits to original, which is the red path in the previous picture, and you can complete them to find an Euler circuit for G. Okay, and so this seems like a nice argument. Well, it's not completely correct at this point, or at least we're omitting some important details. So where did this argument, or where did I leave out some details here? Well, notice that we want to apply our strong induction hypothesis to each component. It's definitely true that each component of G tilde will have fewer vertices, right? So the cardinality of the vertex set has been reduced, so that's good for the sake of induction. But we also want to make sure that each component has the vertices in each component have even degree, right? So I need to check that vertices still have even degree. Right? And once I do check that they have even degree, then this process is valid, right? Because then in each piece, I really do have a smaller graph that meets the hypotheses of the theorem. So in each of the smaller pieces, I can find a circuit. And then, as I discussed for the example picture, right? So the induction would give you these two blue circuits, which you can then join to the red circuit just by, right, as soon as like you hit F, you travel along the blue, and then you travel along red again, and then travel along blue, and then red again, right? Right, so the final technical thing to check is that if I form this subgraph G tilde, that every vertex still has even degree, right? So that's the final thing to prove, and then we'll be done. Right, and so, well, let's suppose that W is a vertex in G tilde. So there's two cases to consider. The first case is that W was not in the red path from the algorithm, from the initial algorithm. Right. Well, in this case, then W has even degree just by the original hypothesis on G. Right, because we're assuming that every vertex of G has even degree. The only issue is that maybe when I formed G tilde, I deleted some edges connected to W that possibly could lower the degree count and make it odd, right? That's the issue. But if W was not in the original path, then none of the edges I removed were incident with W, right? So none of removed edges were incident with W. Right? And so this case is okay, right? So all of these vertices still have even degree because we haven't changed any of the edges that connect to them. Right, so the harder case is case 2, where W was in the red path. Right, so for example, if we go back to the picture from before, maybe W was vertex F, right? So if I go back here, vertex F is in the original path, but when we deleted the red path, we kept in F because F is connected to other things, right? So maybe you can think of W as this vertex. Well, if this is the case, well, remember, once again, we're going to use the fact that if a path travels through W, there have to be an even number of edges in the path through W, right? So right, so there have to be an even number of edges on the red path through W. Even if W was the starting point A, right? Even if W was A, there's still always, when the path travels through W, there's still always an even number of edges that have to be crossing through W. And so therefore, when we delete those edges, we always delete an even number, right? So we always delete even number of the red edges incident with W. Right, and so since we know that W originally had even degree, if we delete an even number of edges that connect to it, well, I'm taking an even number and subtracting an even number from that, so it's an even number, right? So W still has even degree in G tilde, right? And so that completes the technical detail which was omitted before. Right, and so maybe a quick summary again of how this worked. Well, right, so you argue by induction on the cardinality of the vertex set. And so how does the induction argument work? Well, you fix a graph, you run an algorithm, which is kind of like a greedy algorithm, where you just pick an arbitrary starting point for your circuit, and you just keep traveling along edges until you can't anymore, right? And then we prove that if you do this, you always have to end at where you started, right? The only way for there not to be any more edges is if you end at where you started. And so that produces what we call this red path. And then you delete this red path from your graph, and you're left with with some subgraph, which could be broken up into different pieces, right? It could be disconnected. But then you can show that each piece in the subgraph, using the hypothesis that every vertex has even degree, and the fact that a path can only travel through, if a path crosses through a vertex, it has to travel through an even number of edges. You can show that each piece of the subgraph you produce meets the hypotheses of the theorem, meaning every vertex has even degree still. And then therefore you can use induction to construct these two different blue paths, and then you join them together to the red path again, right? And that's the proof. So this is, as you can see, this is a very long and complicated proof. But I think it's worth going through at least once to see that, I mean, these arguments are not trivial, even though maybe geometrically for a particular example, it's maybe for like small number of vertices, it's not too hard to just find a path by eyeballing it. One thing to point out, though, is that you can convert this proof into an actual algorithm, right? And you just follow the process I just described, right? So let's say I give you the problem of finding an Euler path through a graph, and the graph looks kind of complicated. Well, one thing you can do is just start at a particular point and draw a red path in the way that I did until you can't anymore. Well, the only way that's going to happen is if you end up where you started. And while you may not have traversed everything, but then you're going to have smaller pieces where you can do the same process, and then you can connect the different pieces together and use this idea to find the path, right? So this is an example of what's called a constructive proof, because it doesn't just show that the theorem is true; it actually tells you how to find an example for how to solve the theorem in any given particular example, right? So for this proof tells you how to find an Euler circuit. It doesn't just tell you that there is one, right? All right, and so there's a little bit more I want to talk about related to Euler paths, which we'll pick up with on Monday. And I also briefly want to talk about a different similar concept, which is something called a Hamiltonian path, which we'll discuss on Monday as well. Okay.